Okay, pre-lab time. Um, what's going on here? There we go. Something. There it is. Okay, so I'm gonna post these slides, and I'm gonna post um this manual I made. I've been working on this feverishly, so you can, if you want to use the pictures. I'm just too tired to create a separate file, but it's probably useful to have the manual. Now that reminds me, I like to, save this as annotated, I guess. Let's see. So we're going to do the radioactivity part first. And then next week we're going to use the spectroscope. So it's a little different than the past, but I like it because we used to try to have the groups go around the stations, but each station takes some kind of different time, so it didn't work out well. Okay, so my tablet is acting up, of course. Let's see if I can. I'd like to have it. It's just so much easier to write notes onto the slides than to try to type them up. Okay, but we'll get started. So, primarily, radiation. Radiation there's four types: alpha, beta, gamma, and neutrons. And generally, when we speak of radiation, we say alpha, beta, and gamma. One thing we should keep in mind, though, that radiation, light radiates, or your heater radiates. And so stuff I'm going to say is here. So we'll go down the line, and you can see that I wrote up more detail if you like. Alpha particles are helium nuclei. So they, I wonder if I have a picture anymore. Oh, here we go. And, oh no. Okay, anyways, you have a nucleus, and in the decay process, sometimes and they say nuclear decay, of course. Ooh, let's see. So, there we go, alpha particle. Alpha, and it doesn't show the betas here. Oh, there it is down below. Okay, nice. So, we might as well copy this image. I did so much work to be prepared, and now I'm still finding new stuff I could do. Okay. Layout. Okay, so let's paste that. Very good. So, alpha particles are chunks of a nucleus, and in fact, they're a helium nucleus, 2 protons, 2 neutrons. They're very heavy, and they have a charge of 2, and they don't travel very far, and they can be blocked by, say, a piece of paper. In fact, inside smoke detectors in your house, they use a radioactive source with alpha particles, but unless you break it open and eat it, then it's perfectly safe. The alpha particles can't get out of the smoke detector. And, yeah, they generally... this thing is not going to work. They'll go about 20 centimeters in air, or they'll get stopped by several sheets of paper, for example, or a piece of aluminum foil, maybe, instead of a thickness of aluminum. So a beta particle is an electron, and they were things noticed before we knew what they were. We knew what electrons were, and it turns out that what happens is that a neutron can decay into a proton and a beta, and instead of and beta gets released, and the proton stays behind. And then remember that whatever something is a function of the number of protons. Generally speaking, in a stable nucleus, the protons can change back and forth into each other, but the number of protons stays constant. And so betas are essentially, they are electrons, and they are very light, 1/1000th or 2,000. That one, 1,800 times less massive than a proton, and they only have a charge of 1. So it can travel further in air, and it takes more material to shield us from them. And so the way these things lose energy is that they will interact with the electrons, and it's sort of the material that they're hitting, and it's sort of like pulling through cobwebs. Also, if a beta particle is very high energy, it can penetrate into a nucleus, and it can get steered around the nucleus, and then it emits photons. That's called synchrotron radiation. It's also how X-rays are made. It's also called bremsstrahlung, when the electrons come to rest. We could talk about that if you like. And then gammas are photons, and they come out of the nucleus when the nucleus. So a radioactive nucleus is pretty percolating in there, and the nucleons in there can go up and down in energy levels, just like the electrons can go up and down in energy level of an atom, except now the energy levels are very they're very high energy, and then the difference between two levels is much bigger. So you get a photon. They are photons, just like we'll see in the week after. But they're very high frequency, and they're called gammas, even though in general we call a photon a gamma. Gamma radiation is anything that's ultraviolet and above. So it's just that the bare ability for us to see it. It's also what causes sunburns, and so-called ionizing radiation. They have to be above the energy of violet into ultraviolet, and they can start to destroy molecules. Biological molecules have their primary, secondary, and tertiary shapes, and this is what happens if you have a fever. The tertiary shapes fall apart. Well, you can do that with gammas. You can do it with alphas and betas too. The alphas alphas generally don't cause a lot of problems because you simply don't penetrate very far. But betas can come in, and they can liberate energy enough to destroy the tertiary structures, and also change the ident. Well, let's see. Could it change the number of protons? No, it's mostly about disturbing the structures, and so it causes cancer. Now, neutrons can come out. What happens is a strange thing called inverse beta decay. So what the nucleus does is, because it's so strong and positive, it sucks in one of the electrons, and it combines with a proton, and to create a neutron. And also what happens? Oh yeah, wait a minute. I thought there was a positron involved, right? So, well, anyways, typically a can absorb the the beta, and then it combines, and if the neutron's energetic enough, it gets ejected. Yeah. And there's neutrinos, but for us, it doesn't need to be so heavily involved. Now, one of the weird things is that gammas and neutrons need lots of lead and concrete to stop them. Now, neutrons, though, it turns out, can be stopped by oil or wax, and these are these molecules like the carbons, and you may recognize this if you're these hanging with these there's no carbon chains where there's hexane, pentane, that kind of thing. And the oils look something like this too, and the waxes. And it turns out that the density of protons is higher in wax or oil, or even, I think, in water, than it is in lead. Because what happens is you have this lead nuclei, and it's more dense, but you've got the electron shells are so big that when something comes in, there's more empty space between the protons than what there is between in wax or oil. It's more dense in protons, even though it's lighter. And what happens is, because it has no charge, it has to hit a nucleus for it to be stopped. So that's why the waxes or oils. In fact, this is in the Jimmy Carter era. They tried to develop a thing called a neutron bomb that wouldn't destroy anything. It would just kill living things. It was a pretty gruesome thing, but it would only work against civilian populations, because the idea was that it would disable the army, but it'd be very easy to shield the army. You just put wax slabs on tanks, for example, so it didn't go very far. So we're going to mostly speak about alpha, beta, and gamma. Only that. Neutrons aren't a factor, and we don't have the sources we have don't radiate neutrons because they're so dangerous. And even if there's gammas, the sources we have, see what happens is, too, these things damage your cells, but your body repairs it. So as long as the rate of radiation is low enough, the repair goes faster than the damage. Okay, so the big thing you need for your logbooks, for your pre-lab, is what an alpha, beta, and gamma are, and a neutron, and that the alphas don't travel far, stopped easily, betas go through more material, and gammas go the most, and neutrons. Okay, so we're going to be using what's called the Geiger-Müller tube. Geiger-Müller, I'm German, I can't help myself. And it's a pretty simple setup. You have a wire in the middle that's held at a positive high voltage, and then there's a metal can that's at negative, but we usually ground that so that you can't hurt yourself. So we hold the outer can at ground. And let's say something comes in, even a gamma ray will create, because the gamma ray is powerful enough to knock an electron. Remember, these are photons from nuclear energy transition, so they can easily knock an electron off of the gas. And inside here is, say, argon gas, the so-called noble gas. So they get ionized, and then it recombines to form argon again, and it doesn't change if one of them gets ionized. It doesn't form any compounds. So let's see what happens. So an electron gets liberated, and it doesn't tell us what these blue guys are, which is kind of stupid. That's the atom. So the blue ones are electrons that get liberated, and this is the ion that gets created. So the electrons travel towards the wire in the middle. So what happens is that one of these electrons gets liberated, and it starts to travel towards the wire. But what happens is that since the wire here is the electric field gets very intense here. It's oh gosh, I think I should have gotten the equation for it. But the electric field, you must have learned it in class. Electric field at the wire gets very, very high. It's basically something to do with the relationship of the area of the wire and the area of the metal can. And you still have the equal potential surfaces, and they get closer together here. And just like the black paper lab, right, the two surfaces have to morph into each other. So it just basically means the equipotentials get very close together here. So what happens is then the electron's going faster and faster and faster because of the F equal QE force. And eventually it gets fast enough, very quickly it gets fast enough where it hits the air molecule and liberates another electron. And then this keeps going on, and they multiply until we get what's called an avalanche. And I didn't even know what the word Townsend is some dude who described this, I suppose. Okay, so for your logbooks, the structure of this thing, the positive wire in the middle, the field gets very strong as you get closer and closer. There's an inert gas in here, and then also there's sometimes they put a little propane in here, or I forget, there's some other, they could put some other complex molecule, because obviously propane burns, but some other organic molecule. And the point of it is that you can start, this thing could start avalanching, photons get created, and then the photons will make more avalanches, and this thing will just go on runaway. So it needs to have some kind of other gas in there, and a big molecule like that will absorb the liberated photon, but it'll emit it at a lower energy, or it'll absorb the electron. The photon. It'll absorb the photon. There'll be a rise in energy of one of its electrons. It'll decay, but it'll come out at a lower energy, and so that you stop the runaway. So there's this famous curve here, and they call this is the proportional. So the thing is, this is like, you can detect some of the things that come across, because what happens too is that, contrary to this picture, a particle coming through could liberate several electrons on its path. But they may not all avalanche if the voltage is not high enough. And so as you get up and up and up, more and more of them start to avalanche. And then there's this region where changing the voltage of the power supply here doesn't make any difference anymore in the number of ticks you get. Oh yeah, so each time an avalanche hits the wire, that's a signal, a whole bunch of electrons hitting the wire. They go in, and there's a whatchamacallit in here. How does that work? I suppose it's the image charge, but don't worry about it. Every time the avalanche occurs, it sends a pulse down the black wire, and there's electronics in there that turn it into a click, 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 click. And that's, you see that in movies all the time. So we operate it in the Geiger plateau, and if we go above it, then even with the quenching gas, it just would have a runaway. So ours is set for us. I think there's 2 voltages, but the lab tech will set it. We try to make sure everybody who enters class at the beginning goes home, and we don't want you guys worrying about the high voltage. Well, although in this one, I think, 500 volts is enough to hurt you, 1,000 volts. There's a thing called a dead time. It's not something we're going to have to deal with. what happens is the positive ions that get left behind, they drift towards the outer can, and if there's enough of them, they can change the electric field. And so then the avalanche won't happen anymore. And they need time to drift to the outer can, and something on the order of 50 to 100 microseconds, which is a pretty small amount of time. But still is if there's about 1,000 counts per second, the efficiency starts going down. And wow, okay. So, but I put this in because there is a important business for any of you that get into health physics, anything with, if you work around X-ray machines and things, if you have a high rate environment, you can't use a Geiger counter to get an accurate reading because of the saturation effects. And so when you're trying to figure out radiation dose on people, you can't use a Geiger counter. A Geiger counter is just good to let you know something's going on. Okay, so you have this. What this is, the operating range. Dead time. Dead time is simply that positive ions get liberated. They decrease the electric field, and we need to wait for them to get out of the way. But it happens so quickly that you'd have to have thousands of counts per second, and I think the most we're going to see are like 300 counts per second. So that's if we bring the source really close to the Geiger tube. Oh yeah, and by the way, the Geiger tube has a thin window in front. Remember, if we wanted to be able to detect alphas and even the betas, it has some window. I think it's some like mylar with a little bit of aluminum on it, so it's conductive. In fact, you're going to see it's going to have a cardboard cap on it so that we protect it. Okay, so this is a so-called counting experiment. And let's say that we take counts. We're going to be doing this counts for 12 seconds. And we can, every time we start the clock for 12 seconds, and we count the number of Geiger, how many clicks go, we can create a histogram. Oh, this thing is, there it goes. Where is the cursor, though? Oh, something's not working right. Maybe it'll come back. I don't know. It doesn't do this when I'm lecturing. But anyways, if you were to think again of little rocks and boxes, this is a histogram. We're going to get into that about the analysis later. But the point is that if we took enough measurements, like many, and we could plot all of them, you eventually get this kind of smooth curve. And it's symmetric. There's an average value. It's a weighted average, just like number of kids and grades in a class, right? How many kids got an 80? How many kids got a 90? That's a weight, and then divide by the number of kids. So here the average at the top is 200, and the plus minus, well, there's a little trickiness, and it's one of those things, once again, that we take for granted. We say that the standard deviation is the square root of the in this case of the average value, square root of n. Now, it turns out though with Poisson, these so-called Poisson distributions, and this is it looks like a Gaussian, right? And it's related to a Gaussian, but it's when you have integer things, you're counting things. And so penny coin flips, gumballs on the sidewalk, and here radioactive decays. So they're integers. There's no fractional counts. It's not like when you you say you measure a tabletop over and over again with the ruler, it can have a continuous set of values. Turns out, too, though, at a Poisson, if you take enough measurements, it eventually becomes a Gaussian, a normal curve. But in any event, as similar to the sigma of a Gaussian, we say that it contains some like 68%. It's related to the natural logarithm. But for us, one of the other things, though, like if we have these bins where we've been throwing the rocks in, each one of them has an error bar as well, which is the square root of whatever that count is. Now, it would seem that this error would get bigger and bigger, but what happens is that the fractional error of n square root out of n over n, you see that the fractional error gets smaller as you go to more and more counts. And that, it has to be true because we know it's better to take more measurements than it is to take less. You always want to take as many as you possibly can. Okay, so here is that we have the so-called Poisson distribution. When we know the whole population, then we have the standard deviation is square root, and it's plus or minus the square root of the value in the center, the average value. And similarly here, although here it's 197, so square root of 100. It turns out 197, the square root is actually exactly 14, whereas here in 200 it's a little more than 14, but in the manual that I copied, they use 14. Oh, I talked about background radiation. Oh, I forgot about that. Okay, why did I forget that? Okay, I'm going to pause this for a minute. Okay, I'm back. So, you're going to notice that the Geiger-Miller tube, the apparatus goes click, 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 even when the source is not by it. And there's always some background. And that's what that is. It's the background radiation. So we're being constantly bombarded by cosmic rays, which liberate charged particles, which are betas or alpha. Well, mostly there's going to be betas. Natural, there's radioactive. You may have heard of radon gas. I don't know about carbon-14 causing radiation that matters to us. Oh, yeah, it's uptake into our bodies, but that's not a part of the background radiation. There's radon gas is one of the forms of decay of uranium, I think it is. Or maybe it's radium. That's why they call it radon. And let's see. Oh, yeah, in the classroom we may have now, I don't know I just copy-pasted this from the original lab. You'll forgive me. I've been trying to get rid of all the stupidities. And then artificial, okay, let's see. The samples could be stored. The equipment gets contamination. That's not good. If somehow the sources are sealed, but sometimes they, I wouldn't worry about that. Fallout. Oh yeah, we used to test nuclear weapons in the atmosphere. So that's there. And memory of the following exposure to high level. Well, don't worry about that. That's stupid. I guess it's true. I've never heard of it before. So in any event, the background gets added on, and it let's see, what would it do to our histograms? I don't think if it's well, that's the analysis part. All right, so let's see. Random processes, that's the Poisson. All right, inverse square law. So anyways, you say there's background, and let's just get rid of this. It's just so stupid. I didn't even realize that was there. That's just dumb. Fallout from nuclear testing. Nuclear weapons testing. Yeah. What did I always do this wrong? Oh, is this an A here? Oh, weapon. And it's A. Yeah, I don't know how to spell the word weapon, huh? Maybe that's a good thing. Let's see. Natural radioactivity. For example, naturally radio in lead. Well, lead is a decay product of uranium. Okay, that works. Radon gas. It's typically in basements. It does not everywhere. It wasn't on Long Island, but that's beyond the course. Okay, so background. It counts that can cause error in our data, but that's we'll deal with that in analysis. Okay, so the inverse square law. So let's imagine that if we think about the area of a sphere, so like a balloon is around some light in the center, S there, and so if we're at a certain radius R, there's a certain complete area, and then notice, and if we just take a patch like that, if we go out to 2R, we see that because it's R squared, then we get 4 times the area, and at 3R we get 3 times the area. Now, the reason we care about it is you imagine that A, that square labeled capital A, let's imagine that's the window of the Geiger counter, right? So you notice that less of those arrows, which represent particles shooting out, less of those arrows are into that A. And so as we move the Geiger counter further and further back the tube, we're going to see less and less clicks. We're going to hear less clicks. Right? So that means that an intensity is, in fact, we think of intensity as how bright something is, but strictly speaking, intensity is the number of particles per unit area per second. And you see how then the intensity is, well, however those factors are, but that goes over R squared because of the 4 pi R squared nature of the surface. And this is why, if you remember, E equals KQ over R squared, or F equals K Q1 Q2 over R squared, it's everywhere, the 1 over R squared. So yeah, basically this all would go in your logbook. So there's a whole derivation here. And I'm going to go through it, but you don't need to write it all down in your logbook. It's just kind of dumb. But what I want to see is that we can define an intensity at one place and an intensity at another place. And notice we're using this D1 and D2 as our R. And if we do the cross multiplication, and of course, also this factors are going to be the same for both because it's the same source, same detector. We do the cross multiplication, and we see that we can set these two quantities equal to each other. So now we think about D as the distance from the source to the face of the Geiger tube. But what happens is that since the Geiger tube has that wire through the middle and particles can come in and they may ionize here or they may ionize there, they're going to ionize in different places. especially if the particle is traveling and it hits an argon molecule and it could just stop. So the ionization is going to be distributed around here, and X is if we took a weighted average of not W. Let's see. X equals the charge times the X, and this is say it's X average, I suppose. So QX, oh yeah, Q1 X1, that's what I want. Q2 X2 divided by the total Q, and that would be the average place where it takes place. And because the distance was we're going to bring this thing, that distance X is a significant fraction, we have to take it into account. Okay, so we substitute that in, and we crank the algebra handle, and so we will have the situation where we have some intensity we measure at some position 1, and then we'll have position 1, position 2, position 3, etc. So we'll see that so this would become 1 over square root of I sub I, for example. And then let's see, the D2, what happened? Oh, there it is right here. So that would become D sub I. And so notice that this is a constant value. Doesn't matter what X is. This is some whatever it is, this is a constant. This is also a constant. And so that becomes our Y equals mx plus b. And so we can plot D2 and 1 over the square root of I, and I, whatever the place. I guess I have to clean that up too. And let's see, inverse, yeah. Although we're not going to use a trend line. There's all videos for this, and we'll go over this. And what happens is then we can do an R-squared test on this, and if that is correct, that means that the inverse square law is valid. So we're going to test the inverse objectives. Geez, see? Okay, so we're going to learn about radiation types. Oh, I worked so hard on this and I forgot all about objectives. I think I have it here. Let's see. Yeah. Okay. So on top of just learning about what the radiation types and what's a Geiger tube, a Geiger counter, and then we're going to explore random process, the statistics of random. That's the Poisson. We're going to make our I'm going to teach you how to write how to make a histogram. And that's already a video already made, but don't let this freak you out just yet. And we're going to test the inverse square law, and then we're going to learn about what a half-life is, and we're going to measure it. Okay. Back to where we were. And half-life, yeah. So what do you need in your, you can just say that we start out with, so we took from before, we start out with this here. So you could put a little bit of the derivation, but I wouldn't put all of it. And then we can do the cross multiplication because we can, give me a minute. Right, we're going to say, instead of just going to I2, we're going to have an I3, I4, I5, but we can measure I1, it's fixed. We measure D1, it's fixed. Then we set a D2, which is where we're going to put the source, a distance away from the detector, and then we're going to measure the intensity at that. So we can take, and then adding in this to take into account the average position of the created charge, we can create this equation, and we can plot these things and make a straight line fit and do an R-squared test. We can do a fit, and the R-squared test, and then also we can use the y-intercept to get x. Okay. Here it is, sorry. And another thing we're going to do, see, this is the same equation from earlier. And I don't know if we're going to do it like this or we're going to use with the x. Maybe once we know x. I'm really tired. It's almost 7 o'clock. But we can make this plot, and it should be a -2. Yeah, I mean, this is another double check. I think that, and we could do an R-squared test here. But this one is the nice one that basically R-squared test is going to prove to us. All right, so then the last thing we're going to do is we're going to study half-life and exponential decay. So whenever you have a situation where you see you have some population, and say it's a group of nuclei, and they all have an equal probability of decaying, and they don't know anything about each other. I mean, it's not, I suppose, oh, there goes the frickin' tablet again. This, I guess this connector at the, here is what's to blame. Pissed me off. But anyways, a certain fraction of them are going to decay, and that's fixed. And for a given time. So you see here, I've got it set like here. First of all, the number that decay divided by the number that are in there, you see that, give me a minute. Right. So we put it, I'm missing something. Let's blow it. This is one of those things that I know so well that I would just you just take it for granted. Anytime you have a situation where there's an equal probability to decay, a certain number of them will decay, and if we have if we assume, this is not working, but if we assume that delta t is constant, then at the next click, this fraction, the number that decay over the number that are there, will stay constant. And notice that there's less of them here, and less and less and less. So whenever something like this, the number of decays, is dependent on the number that's there, and that in fact itself is a function of time, then you end up with calculus, you get this exponential here, e to the minus, and in this case it's decaying, so it's e to the minus lambda t, and we just define lambda as the decay constant. And I don't have my pen to write here. So, where was that? I'm gonna pause this for a second. All right, maybe my tablet has decided, it's decided to come back. So let's see, delta n over n divided by delta t equals lambda. Right, so the fraction that decay divided by the number that decay divided by the number that exists per time is a constant. And so, right, so then if you plot that, it looks like that. And so this is if this is the case, you end up with this. It's just a rule of calculus. It's differential equations. I guess you integrate that. I'm so tired right now. So anyways, here's what, if you think about it for a minute then, the number that is going to be there after a tick of the clock, so that's this one here, this n, and I divide by the starting number, so instead of calling n sub 0, I'm going to call it n sub I, and then for every tick of the clock, and you could also just call that t sub I, but anyways, in this case, you see that this fraction stays a constant. That's pretty neato. Now, we can say that we can define something called the activity, which is the number of counts per second, and that's what we're going to be measuring. Don't forget, we don't know what n sub 0 is, and we don't know how many nuclei there are in there. We just know we're going to measure a certain number of ticks per second, or in this case, we're going to count the number of sixes in dice. And so, but it follows the same rule. Boy, I'm sorry to do. So anyways, if you have a situation where the number of things that decay is dependent on the number that's there, so I'm going to sum this up quickly. The number of decays is a function of the number of things, and number of things that can decay, number of things decaying, and that means then this is when you have an exponential decay. If these things were like leaving out of a gate, so they had to wait their turn, then it would go down linearly. But because a certain number are going to decay here as a function of how many are actually there, and then a certain number here are going to decay as a fraction over there, and that's constant each time. But the number that decay gets smaller and smaller, of course, because the number that are there is smaller. And that's where you get this exponential. And basically, you can decide any one of them is the starting point. Oh, wait, I'll do that on the next slide. So we can define this thing called a half-life. We can pick anywhere on this curve. I just happen to pick right here, and that's at about 170. And then there's a time here, t1, and then I find another place that's half, 85, and where the two cross, these two straight lines, that's my t2. And so this delta t, So T2 minus T1 is the half-life right here. And again, you can start anywhere. We did this with the capacitors, if you remember. And you'd find that this delta T, if you drew it more carefully, the half-life is still going to be the same here. Now, in fact, there are ways to do the fit here and extract this. But what we can do is we can take our start equation, and then we can take the logarithm of both sides. We end up with here, and you see here, once again, we have mx plus b. So you see there's the y-intercept. That's logarithm of a0. That's not quite so important, but since we're going to be using a big pail full of dice, we can double check and see there's a relationship between a sub 0 and n sub 0. So we can see if we get the right answer. But that's analysis. So if we do these, we make we let the dots go in a line, and we can determine lambda, and then there's a relationship between lambda and the half-life. Let's see. Right. We start off with this. There's the derivation. But at the end of the day, we see that once we measure lambda, then we know the half-life. We also know tau. I forget what tau is called. The lambda is the decay constant. But a lot of times people write it as T over tau instead of lambda T. But that's for the future. It's already, 52-minute video. Okay. And let me double check. Did I cover everything? Yep. Okay. So that, yeah, you need to know all this stuff before, and I still have to go over it with you in lab class what data we're going to be taking. Okay, I'll get this up on YouTube.